Welcome back. This is the second recording of section 3E. We're going to continue our discussion in that section. And here we're going to begin to produce a new concept called the quotient space. In order to introduce that one, let's first define what it means a vector plus a subspace. So here, let me share the screen here. All right. So this is the one definition from the section 3E here. So capital V is still a vector space, and then the lowercase v here is a vector. Usually you can, if you fix the v, right? So then you talk about the one v there. So it's a lowercase v here, taking any vector from the vector space v there, and U is a subspace of v. And then V plus U, so the first letter there before the plus sign, this V is a vector from the V space, and U is a subspace, so it's at least a set, but it's actually a subspace here. And then, so this is a subset of V defined by this fashion. So your V is a fixed vector, and then you let U, the vector U here, run through the entire subspace U. So every possible vector in the subspace U will add with the V here. And then when you add all this together, you collect all these vectors, the sum vectors, and then that becomes a new subset of V, become a subset of V. So this is a I think it's better to use an example to kind of explain this. And let's try to use an example in R2 to explain this, because that one we can graph it. So this example is, I think, extremely important. So we're going to use that again and again in this recording and maybe next recording to help us understand the different part of the section 3E here. So this is the example, I think, 380 in the book. So we're going to consider a straight line in R2. So suppose this capital U is x and 2x in R2, and of course x is an arbitrary real number. So if you check this first, or you can check this U is closed under addition and scalar multiplication, right? Very easy to check that. And then, of course, I want x equal to 0. 0 is also there, so it's a subspace of R2. And graphically, what this U is trying to tell us is this is because the second component over the first component, the slope is 2, right? Except x equal to 0, that's a origin. So this is a straight line. The slope is 2, and then also going through the origin. So this is a subspace. U is a subspace, right, of R2, and U represents a straight line with a slope equal to 2, and this straight line going through the origin, 0, 0. So that's what this U looks like. Now we're going to pick up any vector here. So we're going to, in this case, we're going to follow the book later on. I may change something a little bit easier to work with. But let's consider a vector. I think the book used 1720, this ordered pair, and then plus U, right? So then what this really is? Well, this one geometrically, that is shift this straight line horizontally to that vector at 1720. So in other words, this one here is our original U. This is our U. And then, somewhere, I don't know, maybe, somewhere here, this is like a 1720. And then, so then this parallel line here, this is a 1720 plus the U here. All right. So then this dot here is ordered pair. Maybe I should actually change the color here, so to just make this a red point here. So that one is a vector or it's a dot. That's a 1720, and then this entire straight line going through that one there is a 1720 plus u. That's what this looks like. All right. So looking at this specific example, immediately we have a couple of observations here. One is typically if you have a fixed vector plus a vector subspace, you still get a subset. It's not just like one or two things there, and most likely there are infinite many things here because along this straight line there are infinite many vectors here, right? But this one, this new thing here, this v plus u is not, or it could be, but most likely, in general speaking, you cannot assume it's a subspace, right? How do you know this parallel line is not a subspace? Well, at least the 0 is not there. Our original one 0 is here, and then this one not even including 0, right? So, there are three things we need to check. 0 is there, it's closed under addition, it's closed under scalar multiplication. Probably in this case, none of them satisfied, but the easy thing to see is 0 is not here. So this is not a subspace, it's a subset of R2. So this is a subset of R2, but not a subspace of R2. All right, so keep that in mind. And so obviously, pick up a U, pick up a subspace U, pick up a V. We could, by changing or even your U is fixed, but you're changing the V, you're probably going to get different lines here, right? For instance, if you change the from like 1720 to something like -2, -3, then you're going to get something on the other side, another parallel line here. All right. So then that leads us to our next definition is any thing can be written or recognized as a vector v plus u. This we give it a name called an affine subset of v, and then all this together, or we're going to call that something like a quotient space, but then this is a parallel. At least here we can say it's a parallel. All right. So let's go to the 381 here. This definition here saying, change the color here. So 381, there's a new definition here. All right. So an affine subset of V, right, is a subset of V of the form V plus U, right, for some V in V and some subspace U of the vector space V here, right? Subset of V, okay, it's a affine is that. All right, so this one thing, and also for the vector in the vector space V, and if you a subspace of V, right, the affine subset V plus this subspace U is said to be parallel to U. All right. So I think, of course, the terminology here is a new thing, right? Affine subset, but the parallel part, hopefully everyone see that example above. We can still see the top of the screen there to kind of demonstrate why this thing we call a parallel. Of course, we use the R2 here, right? R3, you could say, well, I have a plane, then I can, add a vector onto that plane. or I have a plane go over the origin, and then I add a vector, so shift that plane, and make the plane parallel to the original one. That's also a good example, but that's probably hard to draw. Right? So we're going to stay with the example in R2 here. All right. So then let's add an example here saying just formally saying this 17 plus 20 plus u are in the example above. I think it's 381, or in the example 380 probably. In the example 380, right? This is an affine subset of R2. Or of course, it's a subset, but it's so special, can be written in this specific form. So we call it the affine subset of R2, and it is parallel to the U. U is the straight line going through the origin, the slope is 2. This one is also straight line, the slope is 2, but not going through the origin, going through the 1720, that point. All right. Now, if we collect all this in together, that is our quotient space. Is if you have a fixed U, which is a fixed subspace of V, then the quotient space, right? So actually we need to, right now I think we call it a space because eventually we're going to equip it with the addition and the scalar multiplication and show it's a subspace, it's a vector space, right? So this is space. We use this notation is V over U, or V divided by U. This is the set of all affine subsets of V parallel to U. In other words, this V over U, this quotient space, is, well, your U is specified, your V is specified, right? But you let your vector, the small vector V here, run through every vector in V. So then altogether, right, because each V plus U is going to give you an affine subset, or at least a subset, right? Of course, one problem we're going to explain later is even your V is different, maybe the V plus U will end up the same. Or the other way to say that is, for one affine subset, the representation is not unique, right? You could do a different V plus the same U, you get the same thing, right? That creates a problem for us when we try to define this, for instance, like addition or scalar multiplication, right? So which representation you're going to use, and we're trying to, show that it's independent of the choice of the representations. But right now, the way to think about this is using that example. Right, so we're going to use that example there to say, well, if this is your U, it's the same one, all right? So this is the x2x in here, or x in R. So if this is your U here, right? So when you let the V be anything in your R2, any vector in R2, and then when you add this together, obviously that's allow you to generate any straight line with slope 2 in this plane. So then you're going to have, one here, you're going to have one here, all right, and then probably one here, probably one here. So all these ones, actually there's no gap there, right? Because, you just, this entire straight line being kind of, the way you look at it, kind of divided all at the same time composed by all this, one by one, all this straight lines, the slope is the same, is 2. So all these lines are parallel to each other, but except the original one, none of them is actually a subspace. It's a subset. It's an affine subset, all right? But altogether, that give you this quotient space is the R2 here divided by the U here. All right, so that is the collection of all of them, all right? So that's give us some idea, like, specifically what that quotient space looks like. So the other thing to keep in mind is each straight line is an element in this quotient space. Your quotient space is not just a vector 1720, it's not just something like 0, 0. No, each element in this R2 divided by U is a straight line, it's a affine subset. All right, so you will have every single line here, the slope is 2, is one element here, or in this quotient space. All right, so then what we're going to do next, I read here. So our next goal, all right, is to make this any, generally speaking, any vector space V over a subspace U here, or make this into a vector space. Vector space. But as I mentioned a minute ago, right? But the challenge is, the one affine subset, may have many different representations. All right, so I'm going to add an example here, still use this straight line example to kind of explain this. All right, consider this one we did before, right? So this is your U, which is this x to x thing, all right? And then let's add something here, right? For instance, if we have a 5 plus U, 5, 0 plus U, right? So then this just means you take this straight line, slope is 2, you move to the right-hand side, 1, 2, 3, 5, so you draw the same slope, all right? So we have 1, 2, 3, 4, 5 here, and so this is your U, all right? So this is your original U here, and then this one here is a 5, 0 plus U, right? However, of course, now we use this point here, all right? But you can choose any other point on this straight line, or on this new line, and add with the original U, you get the same line here, right? So for instance, the 6, 2 plus U is equal to 5, 0 plus U. All right, and you can draw, find the 6, 2 here. 6, 2, you go here, go 1, and then go up by 2. So obviously 6, 2 is here. All right, so this is a 5, 0. This is a 6, 2 here, right? Or you can say, well, I want to go, go probably the other direction. I can say the 4, negative 2 plus U is also equal to 5, 0 plus U, also equal to 6, 2 plus U, right? Because if you go back to the 4, then this go down to negative 2 here. So this one is like a 4, negative 2 here. So actually there are infinitely many ways to represent the same subset. All right, so that's the problem, right? So we're trying to show is, well, it's that does not matter, right? So when you define the addition, when you define scalar multiplication, anyone you use, all right, and then the representation, it looks different, but you're going to end up with the same subset. So that's what we're trying to show here. In order to accomplish that, we need to prove the proposition. There are 3 things are equivalent. So we're going to prove it in this video, and then we're probably going to make another recording for the rest of the stuff there. All right. So let's look at the 385, saying the affine subsets. I probably should write this statement first. All right. So this means the affine subsets are parallel to the same U, or then they're either parallel or they just overlap the same. So that's the essential of the statement here. So suppose U is a subspace of a vector space of V here, of V. And if we have 2 elements belonging to V, right, then the following are equivalent. So there are 3 things we're trying to prove they're equivalent. A is if the difference of V minus W or W minus V is in U, and B is the element of V plus U, capital U, is the same as element W plus U, and the C is the V plus U. This is a subset of V, or of the vector space V, and then intersect with W plus U, this is not empty. So those three things are equivalent. All right. Especially for us, I think the B and the C, their equivalence of B and the C are important because that tells us if there are two things are they not the intersection is not empty, then they're just the same. All right. Or if they have the two representations there, all right, and V plus U equal to W plus U, then that tells you, all right, then these two things intersection is not empty. All right. So, but usually we are trying to say is, well, as long as they are not, they have one thing overlaps, the entire thing, the two things are just the same. All right. That's what the C tells implies B. And here we have three separate statements. Right? So remember, we proved like the biconditional statement many times up to now, right? If and only if. All right. So if you have P, if only if Q, you assume P, prove Q, and assume Q, then prove P, right? Now in your discrete math class, if you have multiple, right, more than two, like 3, 4, 5 or more, are equivalent statements you're trying to show they're equivalent, then usually one strategy we do is we construct a loop, right? Maybe like A implies B, B implies C, C implies D, D implies E, E implies A, right? So you go through the loop, right? So the order of the loop does not matter, but you're just trying to make sure that everything is covered, right? You can have if you have A, B, C, D, you can also do, well, I start with A implies C, right? And then C implies B, and B implies D, D implies E, E implies A. That's also fine, right? But you want everything in that loop, right? And here we have 3. So we're going to follow the book. We're going to assume A, prove B, assume B, prove C, assume C, prove A, and then once we construct this loop here, all right, the strategy of the proof is we're going to assume A, and then use that to prove B, and assume B, use that to prove C, and then assume C, use that to prove A. All right, so then this implies A, B, and C, they are equivalent. All right, that's a very, very typical way to do this in the when you have multiple statements. All right, I think even in the linear algebra, you probably, when you study like the square matrices are showing like the determinant not equal to 0, means this square matrix is invertible, right? And then that means maybe like the AX equal to B always has a unique solution, and there are multiple like statements there, and then you can assume one, prove the other, and so on, right? Do a loop, right? So you've probably seen this even in like a linear algebra class before. So let's construct the proof here, all right? So we're going to go from A to B there, all right? So we're going to assume, all right, V minus W in U, and then we want to prove V plus U is equal to W plus U, right? So how to prove this? And remember the definition is this, right? What is the, so first the V plus U is a subset, right? And the W plus U is a subset of V, right? So each of them is a set. So if you're trying to show two sets equal to each other, right, you want to show one is a subset, or maybe the left-hand side is a subset of the right-hand side, and then the right-hand side is a subset of the left-hand side, then they equal to each other, right? That's first thing, keep in mind. And then also, to show one side is a subset, you take a generic element there from the left-hand side, and then show that also equal to the right-hand side, and then vice versa, right? So that's our strategy. So in order to prove these two sides equal to each other, right? So let's consider this. We're going to take a generic element from the V plus U, right? So let's consider V plus lowercase u here, right? And so that's an arbitrary element in the V plus the capital U there, all right? And you want to show this belonging to the W plus capital U. What do you mean that belonging to the W plus capital U? That means this element can be written as a W plus some element in U there, right? So then how do we create that? Well, let's consider equivalent algebra, very simple algebra here. Write a lowercase w, and then we have the v minus w, that way you cancel the w, and then plus the u there, right? So this is just the equivalent algebra here. W minus w is 0, so it's still v plus u there, all right? Well, remember, since the v minus w in u, this is our assumption, all right? And u is closed, is a subspace, is closed under addition. Then this v minus w plus u is still belonging to u, because v minus w is in u. Of course, the lowercase u, the vector is taken from u. So if you add two elements in the capital U together, it's still belonging to capital U. All right. So then, therefore, so the v plus u, which, all right, equals w plus an element in u. So this is w. This parenthesis is an element in u. Is w plus the capital U. All right. So this v plus is a subset of w plus capital U, and similarly, all right. So we can prove w plus capital U is also a subset of the left-hand side. All right. Thus, we have these two equal to each other. Oh, equal to each other. So A implies B. All right. So B implies C. All right. So what is B, right? So let's take another look here. B is V plus U is equal to W plus U. If that is our assumption, well, then this intersection is just the same as either the V plus U or W plus U. So of course it's not empty. All right. So then this is obvious. All right, nothing we need to do. All right, just observing the assumption that's of course automatically imply what we want. All right. So now let's from the C to the A here. In other words, we're going to suppose C is the V plus U intersect W plus U is not empty. We want to prove the V minus W is in U here. Okay. So by our assumption, so what we mean this intersection is not empty, right? Well, not empty means you can find a common element belonging to the V plus capital U and also belong to the W plus capital U, right? So if there is a common element from the both subsets here, then that means there exists V in V, U1 in U, W in well, the V and the W, we probably just say U1 in U and the U2 in U, such that because the V and the W are already fixed, right? Such that the V plus U1 is equal to W plus U2. All right? Because there is a common, at least one common element belonging to both subsets. So this element, this equal sign means this element, we're referring the left and the right hand side of the same element. That element, if you view that as the element in the V plus U, then that can be written as V plus some U1. For the same element, if you view that as a vector in the W plus capital U, then you can write as the W plus some U2. All right, and U1, U2 are both lowercase the letters. All right, so these are the vectors there. And then that tells us, right, remember what we're trying to prove is we want to show the difference is in U, right? So this is pretty obvious. Then this implies the difference V minus W is U2 minus U1. Of course, well, since the U is a subspace, the difference is closed. The difference is the same as U2 plus negative U1, right? So this is closed under addition. So this is in U, all right? So that's all we need to prove. All right, nothing else. So then, let's use so let's finish the proof, our three things here. So let's use our straight line example to further understand the statement here. We're still going to refer this example a few more times. So we have this, the slope is 2. So this is your u here. Again. So then we said 5,0 plus u, we claimed on the previous page, is equal to 6,2 plus u, right? But this actually like our statement B there, right? You have the V plus U equal to W plus U, right? So this, by our theorem that says this if and only if the difference, well, what is the difference? It's 1, 2, right? This belonging to U. Yes, because 1, 2 belonging to U, because if you let x equal to 1 here, it's 1, 2, right? So that's what we're saying. And then this also means this first set intersect with the second subset, this is not empty. Of course, it's not empty. They're just the same, right? They're the same. And of course, if you start checking this not empty, then you just look at, this one here. This is the u plus 5,0, which is also u plus like 6,2, right? So it's very easy to check they have the common element, right? For instance, 5,0 belonging to obviously the left-hand side, but if you have the 6,2 plus -1, -2, then that's also 5,0. So that's also on the right-hand side. All right, so they're common elements. All right, so hopefully that's help everyone, kind of see what the theorem says. Most of the time, this 385, the way we use that, interpret that is, well, it does not matter, right? So if you are talking about an element of V plus U, then all the other things there are whatever the W use, as long as it's V and the W, the difference is from the U there, then you're always going to get the same affine subsets. All right. So we're going to stop the recording here for the second recording, and then we still need to move on to define something we call a pi, which is kind of like a I kind of call it like a projection map, and then we have that linear map there. I'm going to use that to prove the last result we desire for this section is the dimension of the V over U is the dimension of V minus dimension of U. All right, that's a very beautiful result. So we're going to see that last part in the next recording. All right, see you there.